Hi everyone, welcome to our lesson on the photoelectric effect experiment. The photoelectric effect is something that is actually quite difficult to understand the first time you see it. So we've decided to break down the photoelectric effect into two lessons. This one is focused only on the experiment and the observations that were made. The second lesson on the photoelectric effect is arguably the easier lesson because we give you the formulas straight away. And we look at how those formulas actually are supported by the observations that are made in this lesson here. But this lesson is essential if you've never seen the setup of the photoelectric effect experiment before, or these two graphs that I have to my left here. So the setup is as follows. We have some kind of metal here, a metal surface. We have an ammeter measuring how many electrons are flowing through this green wire. We have a voltmeter, which measures the voltage of the battery, and we have a light source. So basically we turn this light on, and photons flow out of this light here, impact the metal surface, and the metal may eject an electron, which flows from this terminal, this will say electrode, to this electrode, and then continues on around the circuit. So a photon comes in and ejects an electron. We can also use the battery to make observations. So electron here. When we turn this battery on, not only is the photon influencing how fast the electrons are traveling, but we can make this side of the electrode positive, and this one negative. Electrons are negatively charged. They're attracted to the positive electrode and repelled from the negative electrode. So as they get ejected from this metal surface, immediately they have this electric force applied to them, and they begin to slow down. The slow ones will turn around straight away. The fast ones may make it all the way across. We can keep turning up this voltage and keep making this electrode more and more positive until even the most energetic electron doesn't quite make it. And that is the key there. If we turn it up to the threshold voltage, sorry, my mistake, I'm getting mixed up. The stopping voltage here, the stopping voltage, we can basically determine how much energy the most energetic electrons can have. So let's go through some of the observations that were made with this experiment. The first one's simple. Light caused electrons to be ejected from a metal surface. So there is a light electron interaction. The second observation was this. If I keep the same metal surface here and shine blue light on it, I get electrons ejected. But if I go ahead and shine yellow light on the metal surface, I may not get the electrons to eject. So there is a threshold frequency. The frequency of blue light is high, the frequency of yellow light is lower. Once I get past a certain frequency, going in the downwards direction, so I'm reducing the frequency, no more electrons will be ejected from that metal surface. And if I go above that frequency, from blue light to say ultraviolet light, I will still get electrons ejected from that metal. So there is some kind of threshold frequency at which electrons can be ejected. The third one we've discussed, the stopping voltage, tells us the kinetic energy of even the most energetic electrons in a form of energy that may not have been discussed by now, called electron volts. And electron volts is the same type of measurement as joules. It's a measurement of energy. And it's how much energy a single electron will gain after passing through an electric field of a single volt. To go from electron volts to joules, you have to multiply by 1.6 times 10 to the negative 19, and to go from joules to electron volts, you have to divide by 1.6 times 10 to the negative 19. The fourth observation that we make is that the emission of electrons, the ejection of electrons, is instantaneous. Ejection, instantaneous. No matter how low intensity I make this light, even if I make this blue light as dim as I can, as soon as the light reaches this metal surface, I will see an ejection of an electron. Now we go over to our graphs here. We know that at a certain light frequency, so here frequency we'll say is constant, electrons are being ejected, they're flying around the circuit, and the ammeter is registering a current. So we'll say when the voltage is completely off, we get that current there. If we make this electrode over here negative and this one positive, then the electrons that come off the metal surface get extra energy. So we expect just a little bit more photocurrent there. So the current caused by photons ejecting electrons is known as photocurrent. But as we discussed before, if I make this electrode positive and this electrode negative, I reduce the amount of electrons that make it to the end. Some of them have to turn back. So my photocurrent drops. And if I keep making this electrode more positive, finally I get to a stopping voltage, which tells me the most energetic electron. So here is the stopping voltage. Now here is the first, we can say, really strange observation. If I increase the intensity of this blue light, if I make it from, say, the intensity of a light bulb to the intensity of a laser pointer, with the wave model of light, you would expect a greater kinetic energy for the electrons, because you've got a greater intensity light wave incident upon the metal. You expect those electrons to be actually pinging off that surface there. That is not the case. Instead, we find the stopping voltage, which is the kinetic energy of the most energetic electron, does not change, and all we see are more electrons coming off. So this is starting to support the particle nature of light over the wave nature of light. Just because you increase the intensity of that light wave does not mean you're going to get a more energetic electron. Furthermore, if I change the color of the light from blue to, say, green, that's when the most energetic electron is reduced. And we see graphs like this here. So that was low intensity green light, and this is high intensity green light. So our observation is the frequency of light influences electron kinetic energy, not the intensity. And the same graph can be seen down here. I showed you here the stopping voltage changed when we changed the frequency or color of the light. Over here we see the same thing. If the frequency of light is changing in this direction, if the frequency is getting bigger, blue has a bigger frequency than green, then the magnitude of the stopping voltage is also getting bigger. So it looks like this here. That's a linear relationship there. So the energy of the most energetic electron has a relationship to the frequency of the light, and it looks something like this. V naught was equal to the kinetic energy, and it's equal to some constant, we'll say h, multiplied by the frequency, take away whatever this length is here, w. And if we change the metal to a metal that clings to its electrons more tightly, we get the same gradient, but with a greater downward shift. So there's some kind of W value here, which is influencing the energy of the ejected electrons. Basically, all these observations support the particle nature of light. And the final thing we'll talk about in this lesson is that if there is a light-electron interaction and the frequency of the light is influencing the kinetic energy and not the intensity, we can say that there must have been some kind of light particle which is striking the electron and giving it energy. But if any light particle hitting an electron gave it energy, we'd see any frequency ejecting electrons. Since only light past a certain frequency can eject electrons, that means the electron energy, Ek, was equal to the photon energy, take away some kind of work function value, some kind of energy needed to escape the metal. So if our photon energy is not bigger than this work function, the kinetic energy will be zero. We won't be able to eject the electron. Furthermore, if the photon energy is equal to HF, we can see that that gives us this graph here. V0 equals Ek in electron volts, which is equal to HF, take W. This must be the energy of the photon. This must be the work function. Look to the second lesson on the photoelectric effect to see how this formula can be used to solve problems involving this experiment.